Okay, so today's lesson is finding the areas under a curved surface using rectangles. I want to start off with f of x equals 8x minus x squared. And of course, the sketch of that, we would have a 0 at 0 and a 0 at 8. We would have a parabolic shape. And what I want to do is I want to find the area, let's just say from 2 to 5. So I want to take the area on a region from 2 to 5. Okay, so x equals 2 is about here, x equals 5 about there. And again, I want to find the area using rectangles. So I guess at the beginning I'll start with 3 rectangles. So with 3 rectangles, my total distance here would be 3. And if I divide that by 3 rectangles, then each rectangle would have a width of 1. So I would have 2, 3, 4, perfectly even rectangles, as you can see. The bases are exactly 1 apiece. And what I want to do for these particular problems that I'm going to do today are I'm going to use the right endpoint of each one. So on the first rectangle, if you can imagine, if I were to draw a rectangle here, there are really 2 places that I hit the curve. When I draw my rectangle, I could actually make my rectangle line here, which would be what we would call using the left endpoint, or I can use the right endpoint. That's the one I'm choosing for today. I'm going to go up to the right endpoint where it hits the curve, where the right part of the first rectangle would hit the curve, and I'm going to make a point there, and my rectangle would be there. Obviously, you can see that the rectangle's area is going to be a little bigger than the area that's actually inside the curve. Okay, when I go up from 4, I'm going to have a rectangle there, and when I go to 5, my rectangle is going to hit about there. That rectangle actually, having its right endpoint on the parabola, will actually be a little less than the area. So again, we're trying to get an approximation the best way we can. Okay, so what do I need? Well, I need to take the summation of the areas of the 3 rectangles. Well, the width of each rectangle is 1. Each rectangle will have a width at 1. And the value of the y, of where the height of the rectangle is going to be, is whatever f at, and again, looking at these rectangles, the rightmost point on the rectangle is 3. That would find the area of this blue rectangle, which again is going to be a little bigger than the actual parabola. I'm going to add that to 1 times, again the width is still 1, times the height, which would be f of 4, plus 1 times f of 5. And adding those all together, I'm going to get an approximation of the area under that curve from 2 to 5. And just to make sure that you can see exactly where the curve was, I'm going to attempt to make this a little darker. I'm claiming that the area in this black region can be approximated by those 3 rectangles. Okay, well, f of 3, I can do that without a calculator. 24 minus 9, I believe, is going to be 15. F of 4, the value that I get when I plug in 4 would be 32 minus 16, which is 16. And the third rectangle, f of 5, if I plug in 5, I get 40 minus 25, which would be 15, making my approximate area 46 square units. Okay, now my claim is that if I'm going from 2 to 5, and I use 3 rectangles, that's a decent approximation. If I were to use 6 rectangles, I believe that we're going to get an even better approximation. So I'm going to attempt to do the same problem, but this time I'm going to use 6 rectangles. Okay, so again we had an answer of 46. Okay, so I'm just going to draw the part that I'm really concerned with. I think it looked a little bit like that. And I was going from 2 to 5. And I believe the 5 was a little lower. And now what I'm going to do is I'm going to divide this into 6 rectangles. So I still have a total distance of 3, but I'm dividing that by 6 this time. 6 rectangles. So hopefully you can see this okay. 3 over 6. Each rectangle is going to have a width of 0.5. Okay. So let's start taking a look at that. Every time I go 0.5, I'm going to have to make the rectangle wider. Or I'm going to have a new rectangle. So at 2.5, 3, 3.5, 4, and 4.5. Those are assumed to be exactly the same distances. Hopefully they look the same. Okay, so this is 2.5, and I know that the film is going to be hard to see, so I'm going to make these numbers a little taller. I'm going to go 2.5, 3, 3.5, 4, 4.5 as the values along the bottom where I'm going to draw my rectangles. So here's my x-axis, and now I'm going to start to draw my rectangles. Again, this is 2, this is 5, and now I'm going to start drawing them. Again, I'm going to let the right endpoint be on the parabola. So I'm putting my rectangles in so that the right endpoint of the rectangle is on the parabola. And of course you can see that these rectangles are exactly the same length. I'm phenomenal at that. And my last one would happen at 5. I think that the amount of area that were greater than the parabola and the amount that were less than the parabola, again, this thing's been blown up. Okay, I had a much wider span and a shorter area in the other picture that I drew. But I'm promising that the wasted area is going to be a lot less. Okay. For this, that means that I'm going to have to find the area of these 6 rectangles. And the rectangles, I'm going to erase this guy up here. The rectangles would be a width of 0.5 times whatever f of 2.5 is, plus 0.5 times whatever f of 3 is, plus 0.5 times f of 3.5. Again, I'm using the right endpoint of each rectangle, plus 0.5 times f of 4, plus 0.5 times f of 4.5, and do I have a little bit of room left? Plus 0.5 times f of 5. And I'm hoping that that's showing up okay on the film. Okay, now notice that each one of these guys has a 0.5 in it, which means that I can pull 0.5 out in front of a set of parentheses. And inside the parentheses then, I can just write f of 2.5, f of 3, f of 3.5, f of 4, f of 4.5, and f of 5. So I don't need to have the 0.5 in every calculation because I've pulled it out in front. Okay, well, I certainly can do this by hand, but I don't feel like it, and I don't really want you to do it. I might ask you to do 12 rectangles or 20 rectangles, and this calculation is going to be a pain. So what I'm going to do for you is I'm going to show you how to use the calculator to generate these values, f of 2.5 through f of 5. So I'm going to leave the screen and be using my computer off to the side. And I am going to generate these values using your calculator. I'm going to show you how to do it. Okay, here's the calculator with the TI-85 program, or TI-84 program. So what I want to do is I want to put my f of x into y1. And my f of x was 8x minus x squared. Okay, so 8x minus x squared I'm going to put that in y1. And now what I'm going to do is I'm going to set up a table. To set up your table, you're going to use second table set. And what that does is asks you for a starting value and a delta table. I'm not assuming that I'm teaching this thing from scratch. You should have had this at some point. I'm just giving you a quick rundown. The table start would be at 2.5 because that's the first value we wanted to plug in to find our rectangle. And the delta table is going to be 0.5. Delta just means change in. We want to change the x values that we're plugging in by 0.5. Okay, now if you go to second and then over to table, which is just above the graph button, okay, you can now see the values from 2.5. From 2.5 and up. So I wanted to go from 2.5 all the way up to 5, and I need 6 values, 1, 2, 3, 4, 5, 6, and they're all there. I'm going to jot those down so that I can transfer them to the screen and lift that screen again. So I had 13.75, 15, 15.75, 16, 15.75, and back to 15. And we're going to go back to the original calculations we had. And we're now going to fill in all of these values up here. And I guess the best place would be to keep that there. And let's fill them in down here. So I have 0.5. Try to write them a little bigger. F of 2.5, which was my first one, is 13.75. F of 3 was 15. F of 3.5 was 15.75. F of 4, of course, we calculated before, was 16. And then we have 15.75 and 15. And all I did was pull those out of the y values of your chart. Okay, so now we're going to add those together, and we should get an approximation of the area under the curve. So for our decimals, we have 1.5, 2.25. For our numbers, we have 28, 38, 43, 53, 59, 69, 74, 84, 89. So that's going to give us 91.25 multiplied by the width of our rectangles, which is 0.5, all totaling 45.approximately 625. And that's the approximated area using rectangles of the curve 8x minus x squared using 6 rectangles. The last thing I want to say about this is, what would happen if instead of using 6 rectangles, we use 6,000 rectangles? What do you think about the accuracy of our rectangles? Well, to me, I think if we make each rectangle smaller, then the amount of waste per rectangle is going to be much less. And I think our approximation is going to be perfect. Or not perfect, but very, very close. What if we use 6 million rectangles? That's a thought I just want you to keep in the back of your head. Okay, let me set up the next problem, and then we'll continue in a few seconds. Okay, so this time I want to take the function y equals x squared plus 4 and take the area from 0 to 2. And I'm going to use 8 rectangles, just to show you that you don't have to use a 1, you don't have to use a 0.5, you can use really whatever you'd like. So I went from, again, 0 to 2 with 8 rectangles, which means each rectangle would span a width of 0.25. So again, as I look along the bottom here, I would have 1.25, well, I'd have 0, excuse me, and then I would have an x of 0.25, and then 0.5, and then 0.75, 1, 1.25, 1.5, 1.75, and 2. So notice that if I move over a width of 0.25 each time, that these would be my values. But I only need 8 because I have 8 rectangles, and again I'm going to use the right endpoint. 1, 2, 3, 4, 5, 6, 7, 8. You never end up using this first guy over here, which would be the 0. I want my values, my x values, to span from 0.25 over to 2. So let's take the time one more time to go through the calculator. So I'm going to pull down my screen again. And let's take a look at those values on the calculator. So there's my calculator, and as you would expect, I've already taken the time to go into my table set. I've already put the equation into y equals, and on my table start, I started at 0.25, which was the value that I told you we were going to start with on the right, and my delta table is 0.25. Okay, so of course again, y equals x squared plus 4 is my function. That's already in, and you can see that in this area here. So let's look at the y values. I've already recorded them, so I'm going to go a little quicker than before. But I just want you to notice the first one is 4.0625, the next one is 4.25, etc. And certainly x squared plus 4 when x equals 1 is 5. So again, I just want to give you a quick view of the calculator. I'm going to turn that guy off and resume my board work. I want you to notice that all the values have been recorded over here. 0.25 was that 4.0625, and I recorded the right endpoints of all 8. Okay, and again, the idea here is that I'm drawing a rectangle up to the function, and the right endpoint is on the graph. So y equals x squared plus 4 is how that value is going to be generated. So as I said, there's all your values, and the area, or the sum of those, would be 44.75. But remember, those are all my f of 0.25, 0.5, 0.75, etc. Remember, the last step is that I have to multiply by all of the widths of the rectangles. So 0.25 is going to be the width of one small rectangle times the height of each rectangle, and it's been factored out just like I did in the earlier problem. So the answer to this on your calculator would be 0.25 times 44.75, which is 11.1875. And of course, the beauty of this film is you can go as slow as you want, you can rewind, but certainly you should be able to follow this, use your calculator, and generate those values. The last thing I want to say is, or a couple things actually, is if you wanted to do left endpoint, you could do that. If these were your 9 values, if you were doing left endpoint, meaning you wanted your rectangle to have its left endpoint on the curve, then instead of using the 8 values within the green, you would simply be using from 0 to 1.75. There are methods where you use the best rectangle. So you look at it and you say, well, would I rather use the right endpoint or the left endpoint on my rectangle to give me the best approximation? And there's still another method where you use the midpoints of each region. So there's lots of ways to approximate that area if you want to play with it. But again, it's an approximation, and it's only supposed to lead you to one final idea. And let me show you what that is. In summation, we're taking the summation in that last case from n equal 1 up to n equals 8, and we're doing area of rectangle sub n. In other words, the first rectangle, the second rectangle, the third rectangle, all added together. Okay, and where do those rectangles come from? Well, it's the summation of f at x, which tells you the height of your rectangle, times the width of your rectangle. And we were calling that delta x, but, well, we'll call it delta x. How much our rectangle was the width of it. Well, folks, to say that I want to do an infinite number of rectangles, okay, would mean that I really don't want to use a summation because you wouldn't get the feel for it. To use an infinite number, we sort of use a shorthand notion for our summation, and it looks like this, which you will learn to call the integral symbol. The f of x is, of course, the height of each rectangle, and instead of delta x, we choose to use the symbol dx, which you've seen before, which just means the very smallest little difference in x. And folks, this was what you'll learn to use for integrals, and you'll find out that integrals are actually the best method for finding area under the curve. And for our last example, just for the fun of it, this is where your values are for what you're integrating between, or finding the area of the curve between, in this case 0 to 2. The 1 to 8 really doesn't show up in an integral, but when you get to this point, that's where all this comes from. So I hope this helps. Hopefully you have a feel for this and you can do your homework, whatever problems you're given. And I also provided a PowerPoint that I made into a movie format that you can play on any machine. And you can see some other examples worked, or certainly see the stuff written out in case you'd like to take better notes. So that's areas under the rectangle. I guess I'll be seeing you on the next film.